was just taking a short break there to eat a salad. It was very delicious. Anyway, what we're going to do now is possibly the difficult part of the question. We've got to find an expression for d. So if you notice, we can actually just quote the result we just had and replace n with n plus 1. So just like b was equal to this thing here, we're now going to say what d is, but with each n we're replacing with an n plus 1. Okay, so you're summing up to n plus 1 for your kx squared terms. And then you're taking away the n plus 1 equivalent of a, which would be c squared. So that's d. That's one expression for d. Now, how does this relate to what we've been told to relate it to? Well, if we look at the summation, we see that b is summed to n, and this is summed to n plus 1, so it makes sense to just, do this. And split it up, appending the last term here. And then we see, whoops, that's squared. And then we see that this is actually b, some rearrangement of this. In fact, you see this is actually equal to b plus a squared, where we take a squared to the other side, so we're basically making this dude here the subject of the equation, and then multiplying that by n. So that is exactly what that is. That makes a lot of sense, right? Alright, so now we have an expression for d because we already expressed c in terms of a, x plus 1, and n. We already did that at the beginning, so we have an expression for that. So let me try and write down d in one line. It's going to be pretty messy, but here we go. So d is 1 over n plus 1 times that sum there, which we worked out to be n b plus a squared plus x n plus 1 all squared. Alright, so that is the first bit. And then c was this dude here. And we're going to square c. So we have this. Okay, so that's just subbing in our expression from the first bit. Interesting. Now, what are we going to do with d? Well, we are going to do a number of things with inequalities. We want to show when, like how it relates to b, certain less than equal to's. Interesting. Okay, interesting stuff. So it would make sense right now to find a tighter expression for d in order to actually do that. So we notice that both of these terms here are like fractions. So I want to write them as a common denominator. And I'm going to do that. It's probably a good habit to write this outside rather than writing the whole thing as a fraction, and writing a huge fraction of blah, 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 and then having an n plus 1 squared at the bottom. Probably don't want to do that. Probably want to do it this way. It's a little bit neater, using a big bracket. So, I mean, what's going to happen here? We're going to have our n plus 1 times b plus n plus 1 times a squared. Sorry, a squared. So, yeah, that's that, because we have, because we're writing this over n plus 1 squared, we're going to, multiply. It's basically equivalent to multiplying this fraction by n plus 1 over n plus 1, right? So multiplying it by 1 doesn't change it, but each term in there will get multiplied by n plus 1. So the last term that gets multiplied is this x n plus 1 squared. Okay, and then we're going to take away, well, na all squared minus, I'm running out of space, 2na x n plus 1 minus x n plus 1 all squared. So that is that dude there. Now, I mean, what's going to happen now is with this mess, we want to cancel it down a bit. Get something a bit nicer. So we see this is n plus 1 of those terms, and this is one of the terms. So that's going to cancel. We're just going to left with n of those. Okay, so let me write that there. N xn plus 1 squared. Okay, and if we look hard enough, we will also notice that we're going to have our n squared a squareds there, and they're going to cancel. Okay, well, that's left with an na squared. That's what will be left, but our n squared a squareds are no more. Okay, and there's a plus in there. We're still going to have our expression of b, but we're also now going to have it minus 2n a x n plus 1. Alright, and that's what we've got left. This is 1 over n plus 1 squared. Okay. Now, nicely what we notice also, I mean, it's really nice how this actually had a quadratic in it, because it might not have, but it has like a perfect square expression right here. I find this fascinating. Like, why would a perfect square expression appear in a relation of the variance of n plus 1 terms to n terms? I don't know, but like nicely it has, which allows us to say pretty much the rest of what we need to say. We see that d, to simplify this a bit more, I'm going to say that d is 1 over n plus 1 of nb. Okay. Plus n, so we're going to take our n outside of this expression here. Out of these three terms, we see that they actually collect together to form this. All right, and then over, well, it's going to be n plus 1 squared. That's fascinating, the way we were able to take that out. I don't really know why that happened, but there it is. Now notice this, this is probably our favorite expression for d that we're going to use to plug things in and figure things out about how it relates to b. So how does it relate to b? That is really the crux of this question. How are the variances linked? Well, we know that what we're asked to do is find n plus 1 d and show that that's always greater than nb. Well, we can do that. We're going to call our expression star and then refer back to it. So maybe write star and then multiply both sides by n plus 1. What we're going to get is we're going to get n plus 1 times d equals nb plus n over n plus 1 squared. Well, actually, it's not squared anymore because we multiply by n plus 1. Multiplied by this expression. So when is n plus 1 d? When is that greater than or equal to nb? Well, that's going to be greater than or equal to nb if and only if a minus x n plus 1 all squared is greater than or equal to 0. You might want to write some comment in there about the fact that n plus 1 is always greater than 0. Okay? You know, because we're considering n to be fixed positive integers, so that's quite clear. But this squared expression is always greater than or equal to 0, which is true. You know, so therefore n plus 1 d is always greater than or equal to nb. Interesting. Okay, now we're going to take our expression for d, and we want to investigate when d is less than b. So how do we investigate when d is less than b? Well, it makes sense, and you'll see this trait in STEP a lot, is to try and get 0 in your inequality, because that we can investigate this much more clearly than trying to investigate this thing over here, which is quite confusing. Try and draw like a confused guy face, and there's a smiley face. So this is something we're familiar with here. So let's investigate that. So we have our expression for d. So therefore, I wonder if I can select this and move it. Yeah. Let's try and copy that and move over here and paste it in. Yeah, awesome. Didn't know I could do that. It worked. Okay, so now what we want to do is d minus b. So what's that equal to? Well, think of that. That's n over n plus 1 b. And we're going to take away b. And rather than writing take away b, let's add a common denominator to that. All right, and then we'll have our plus n over n plus 1 squared. You know, a minus x n plus 1 squared. So we're going to have that do there. But notice that this is actually can be much more concisely written by putting this in the front, because it's a positive term, and what we're actually going to be left with is a negative term. You see that is just minus 1 over n plus 1 b. And we like writing it in this way because, well, d is less than b, therefore if and only if n over n plus 1 squared a minus x to the n plus 1 squared minus 1 over n plus 1b. It's you know, if and only if this thing is less than 0. Sorry, I should write d is less than b. If and only if blah 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 is less than 0. That's obvious, right? For d to be less than b, this would be negative, which would make this negative. So when is this less than 0? Well, when is it less than 0? It's less than 0 if and only if a minus x to the n plus 1 all squared is less than, well, that's n plus 1 over n b. All right? So that makes sense. But notice this is squared. And if we look back to our question, we should be beaming with joy right now, because this is really leading us towards what we want now. So when is this true? Well, this is true if and only if we take the negative square root of that thing. All right, is less than a minus x to the n plus 1 is less than the positive square root of this thing. And that makes sense because we're not sure whether this expression here is positive or negative, but this inequality tells us it must be bounded between those two values as such. Now what we want to do is, you know, how does this relate to our last question? Well, we want just x to the n plus 1 in there. So we don't want the a, so we're going to be taking a away from both of those terms. It's going to be a minus a there and a minus a there. And then what we're going to do is multiply across by minus 1. And you see the signs will flip. So that's going to be a plus n plus 1 times b all over n. Less than, or sorry, greater than x to the n plus 1. It's greater than a minus the square root of that thing. In other words, we get exactly what we want. We get a minus the square root of n plus 1b over n is less than x to the n plus 1 is less than a plus that square root. Okay. So that's really it to the question. And that's, to look at it from a deeper perspective, that's kind of interesting. We're showing that the variance of n plus 1 fixed real numbers is less than the variance of n of those fixed real numbers if and only if this is true. So if this kind of links the mean and the variance of the other numbers with this number. Now my stats isn't as good as it should be, but this is possibly represented in the central limit theorem in some sense. It's kind of worth investigating, actually. I might go look it up after and maybe put a comment in the video of what this relationship actually is. But I think it's linked to the central limit theorem. Not really sure. But anyway, in terms of a purely step question approach, that result wasn't that difficult to get to. It just, I guess, is a jump from A-level standard with the amount of algebra we had to work through. But, you know, question 1, step 3, 2010, not too bad. All right. Thanks for watching, guys. I hope this was clearly explained. And if not, just give me a note in the comments if you're unclear about anything, and I will get back to you as soon as I can. And if you like this video, share it with anyone who's doing STEP. You know, send me messages if you're struggling with anything. I'll try and do what I can to help. I'm not claiming to be an expert by any means, but I mean, I've sat it twice now. I'm going to my third time, so I know a bit about it. But yeah, hope you enjoyed. Thanks for watching.